My name is Diego. I'm in my last year of the PhD in Sustainable Infrastructure System. And today I'm talking about part of my research, that is the understanding of the formation of woody debris jams at bridge piers. So, what are the effects of this large wood debris that we have? Imagine we have this pier in a river and we have an efflux that is created by the presence of an obstacle and the scour that is associated with the presence of the pier. We have vortices that will generate this scour at the riverbed. But if we introduce woody debris, we have that the efflux will be significantly affected. We have lateral loads on the pier that will be very important in terms of structural stability, and furthermore, the scour is exacerbated quite significantly. Therefore, we can expect that these effects combined together can lead to bridge failure. You can see on the top right the Charles Bridge in Prague, which during the flooding event in 1890 was severely affected and was totally destroyed by the presence of these debris rafts. But the problem is that these bridge failures are very common nowadays. We have another example on the bottom left. This is a bridge in the US, which has failed due to the presence of this woody debris. Therefore, this is extremely important in terms of both flood risk assessment and bridge stability and bridge design. What we know about this woody debris is that most of the studies are based on site observations, which means that little effort has been put on the theoretical and experimental study on that. We have some experimental studies, but most of them are based on scour, which means that we are only analyzing one part of the problem, and in most of the situations, the model debris that were chosen were totally arbitrary and not consistent with the actual shape and size that these woody debris can reach in rivers. Furthermore, we have some guidelines. In the figure, you can see the Australian and New Zealand practice that is suggested for bridge design, which is just guidelines, but they are not actually linked to a research and analysis. They are just arbitrary. So this means that if we want to analyze the effects that these woody debris accumulations have on the current and on the bridge, we need to understand what could be the potential size that these accumulations have and the related variables with that. So the aims and objectives of this part of my research is to experimentally study the formation of this woody debris, so experiments were carried out, test the influence of all the intervening variables. As you can imagine, this problem is extremely complicated and presents a lot of variables related to the size of the debris, the pier, the individual elements, and so forth. Also, a very important part is to develop the ability to predict the size that these accumulations can reach for given variables and flow conditions. And finally, I compared the woody debris accumulation reached with idealized debris with uniform length and diameter and size, with those that have a more real-world mimicking debris, so with non-uniform distribution of lengths. The methodology followed the very classical hydraulics analysis, that is the dimensional analysis. As you can see, the variables that are involved in this process are quite significant. So we have 11 variables, and we use the dimensional analysis to, at first, try to identify the main variables that are involved in the process and to reduce the number of these variables involved. As a first step, I chose as a repeated group velocity, water density, and length of individual debris. This brought to the formation of these dimensionless groups, in which you can spot two numbers that are extremely important for the hydraulics, that are Reynolds and Frown number. But we can further simplify this function, saying that Reynolds at the river scale is uninfluential, so we can disregard it from the analysis. Also, we know that we can't use Reynolds and Froud similarity, so we need to choose between one of them. Furthermore, we can suppose that the pier is single, isolated, so it has no interaction with the boundaries, and that the water depth has no effect, and finally, that the experiments were performed with uniform density. This leads to a much more simplified equation in which we have just 6 variables, and in which we are relating the size of the accumulation, here expressed with the dimensionless variables W over L, H over L, and K over L, meaning width, length, and height of the accumulation, with other variables that are the Frown number, the ratio between the diameter and the length, and the ratio between the length of the debris and the diameter of the pier. So experiments were carried out at the Chilward flume here in Southampton. The flume is 22 meters long and 1.375 meters wide, so it's quite a pretty big flume compared to the standard flumes that we can find in other reports or studies related to debris. Each experiment was performed under uniform flow conditions, so there was no flow change, and measurements were carried out by 3 cameras, one ADV to measure the flow velocity and flow characteristics, and one ultrasonic sensor for the water depth. You can see in the pictures the layout of my setup, so you can see the pier in the middle and the cameras that were used and the ultrasonic sensor. The debris were modeled using natural sticks, so to give a more real-world approach, I use the sticks, so we can use the sticks as a scaled model for real trunks and trees that we have in natural rivers. There were 3 different types of uniform debris and 7 types of non-uniform debris. The difference is that uniform debris are simply debris with the same length, same diameter, same characteristics. Non-uniform debris are those that you can see in the picture, so with lengths that were following a certain probability distribution based on published data that could resemble more in detail what you can find actually on a river. A total of 322 experiments has been carried out for this. There are other experimental sets that are not shown here, so the number is around 700 experiments in total. And the sticks, they were individually dropped with constant frequency into the flume, and they were left free to accumulate at the bridge pier. Okay, here are the results. So you can see the video here in which we have 3 different stages of the debris growth. The first stage is called unstable. As the name suggests, in this stage, the accumulation starts to grow, but debris can be easily mobilized, so it's very unstable. At the same time, the pace of the growth is very high, so you will have that this accumulation will grow in a very short time. Afterwards, we have a more stable accumulation. In this case, the accumulation is pretty stable, it's not moving, and the growth of the rate of the accumulation is pretty small. And we generally have the shape that is a half cone. And finally, we have a very final stage that is called critical. In this condition that is about to show, we have that the accumulation starts to oscillate about the pier, and with this oscillation, the accumulation is eventually drifted away. So we have a proper accumulation failure. This is extremely important because this behavior was observed for all accumulation, which means that this process can be regarded as the upper limit of an accumulation growth. Here you have plotted the results of our dimensionless variables. So on the top you have the width over the length of individual debris, in the middle the height, and on the bottom the length. They are synthesized there in the picture on the top right. We can see that there are marked relationship between these dimensionless variables and the debris Frown number. So you can see that for width and length, for low Frown number, the size of the accumulation is the maximum, whereas with increasing Frown, the size decreases. The opposite behavior is shown by the height. So the height is very low when we have low Frown numbers, whereas it grows when the Frown number grows. In this picture, you have the uniform land debris. In the next picture, we have the non-uniform land debris. As we can observe, on a general trend, we have no differences. The main difference is that for uniform debris, the size of the accumulation is much bigger than non-uniform debris. Here we can reach, for example, for the width, a maximum of 1.5. If I go back to the uniform debris, we reach values around 3.4. So we can see that if we have accumulations formed by uniform debris, so debris with the same length, we will have accumulations that will be significantly larger than those formed with non-uniform debris, in which we have a key element, so a large element, and then smaller elements that are mixed together. Anyway, in the general trend, we can see that there is still this dependency on the Frown number. So this means that the debris Frown number is the main parameter that is driving the size of these accumulations. Therefore, in conclusions, we have that these woody debris accumulations, they grow and according to a three-phase scheme in which we have unstable, stable, and the critical stage. The most important thing is that the critical stage represents an upper limit for these accumulations. This critical stage, which means the failure of the accumulation, is reached for all of the tests that we had. So it means that it's a process that is always occurring. And furthermore, we know that the accumulation size depends on the debris Frown number. So knowing this debris Frown number can give us an idea of the expected debris size, the accumulation debris size that we can have at the bridge here. Furthermore, we have that uniform debris will give accumulations that will be significantly larger than those formed by non-uniform debris. And finally, we know that we don't have enough data at the moment available to predict woody debris accumulations, but with these experiments we have a data set which can be used to simulate and can pave the way to predict potential woody debris accumulation at bridge piers. Thank you for your attention.